Welcome everyone to this video by Learn Civil Engineering, where we will be learning about internal forces. In previous videos, we have only covered structures subject to axial forces, where the internal forces are parallel to the axis of the members, and so each member is under tension or compression. In this video, we'll be covering the more general concept of internal forces and how to compute them in structures, working through an example to apply this knowledge. We will then introduce the concept of internal force diagrams, which will prove even more useful for structural analysis, and we will finish the video with a couple of examples applying this theory. In general, the bars that make up a structure carry the loads applied to the structure to the foundations. As a very simple example, consider this structure consisting of a single bar that is free at point C and fixed at point A. If we were to apply a force, F, to the free end of the bar, to guarantee equilibrium, we would have the following support reactions at the fixed support. As the bar transmits the applied force to the support, internal forces are induced in the structure. Whereas within truss structures we saw that bars can only carry axial forces, which are forces parallel to the axis of the bars, bars within general structures can carry axial forces, shear forces, and moments, where shear forces are forces perpendicular to the axis of the bars, and moments cause bending moments in the bars. Therefore, at point B in the bar, there will be an internal force parallel to the bar, an internal force perpendicular to the bar, and a moment. When computing internal forces, in order to guarantee equilibrium, we must only consider the part of the structure to the left of the section, or the part to the right of the section. Looking at our simple structure, for example, cutting the bar at point B, we can consider the structure to the left of the cut, or to the right of the cut. As we cannot consider the whole structure, we will focus on the left side. For this example, we will imagine the structure has a horizontal support reaction of 2 kN acting towards the left, a vertical support reaction of 5 kN acting upwards, and a moment of 18 kN acting in an anti-clockwise direction. We will also imagine the length of the bar from point A to point B is 2.5 meters. Now, as we have cut the bar at point B, we must replace the right side of the structure with the existing internal forces. As these are all unknown, we will assume sensors for them, and writing them onto our diagram, we have the axial force, N, the shear force, V, and the moment, M. To compute the unknown internal forces, we must apply the conditions for equilibrium, where the sum of all horizontal forces must be equal to 0, the sum of all vertical forces must be equal to 0, and the sum of all moments relative to a point must be equal to 0. And we have chosen that point to be B. Taking the x-coordinate direction to be positive then, the sum of all horizontal forces is equal to n minus 2, which equals 0. Taking the y-coordinate direction to be positive, the sum of all vertical forces is equal to v plus 5, which equals 0. And finally, taking the anti-clockwise rotation direction to be positive, the sum of all moments relative to point B is equal to 18 minus 5 times 2.5 plus m, which equals 0. And each of these equations only have one unknown, and they're very simple, so we can see from them that n is equal to 2 kilonewtons, v is equal to negative 5 kilonewtons, and m is equal to negative 5.5 kilonewton meters. Having computed the internal forces at point B in the bar, we can see that if equilibrium is guaranteed for one side of the structure, equilibrium will also be guaranteed for the other side of the structure, considering forces of equal intensity but opposite sense. Therefore, we can write out the positive notations for internal forces in a bar. For structural analysis, considering a bar which is oriented from left to right, the positive internal forces are denoted like so, where the positive axial force is acting outwards from the centre of the bar, subjecting the bar to tension. The positive shear force is acting downwards on the left and upwards on the right, both being perpendicular to the bar, and the positive moment is acting in the clockwise direction on the left of the bar and in the anti-clockwise direction on the right of the bar. Bars are typically oriented from left to right, except for vertical bars, which are oriented upwards, which means the bottom is the left and the top is the right, like so. And using these principles and notations, we'll be able to compute the internal forces in any section of a structure. Let's have a look at a more complicated example. Consider this structure, which consists of two bodies: a straight bar from point A to point B, and a bent bar connected at point B with a free end at the other end. the structure is being supported by a hinge support at point A and a roller support at point B. The dimensions of the bars are shown in the diagram, and a uniformly distributed load is being applied to the entire length of bar AB, acting in the downwards direction and has a magnitude of 10 kilonewtons per metre. There are also two concentrated loads being applied to the structure at the free end of the bent bar, a vertical load of 6 kilonewtons acting in the downwards direction, and a horizontal load of 10 kilonewtons acting towards the right. Finally, the weight of the structure is negligible, which just means we don't need to account for the weight of the bars. Using the principles we have covered, we are going to determine the internal forces at point C, which is at the middle of bar AB, and then the internal forces at point D, which is at the middle of the vertical section of the bent bar. To start off, we must calculate the reaction forces at the supports. At the hinge support, there will be a horizontal and a vertical reaction force, and at the roller support, there will only be a vertical reaction force. To calculate the reaction forces, we must apply the conditions of equilibrium for the entire structure, where the sum of all horizontal forces must be equal to 0, the sum of all vertical forces must be equal to 0, and the sum of all moments relative to a point must be equal to 0. Taking the x-coordinate direction to be positive, the sum of all horizontal forces is equal to ax plus 10, which equals 0. As ax is our only unknown for this equation, we can solve it now, and doing so, ax is equal to negative 10 kilonewtons. Taking the y-coordinate direction to be positive, the sum of all vertical forces is equal to ay plus by minus 10 times 4 minus 6, which equals 0. Now we have two unknowns, so we'll come back to this equation in a second. Finally, taking the anticlockwise rotation direction to be positive, the sum of all moments relative to point A is equal to negative 10 times 4 times 2 plus by times 4 minus 6 times 7 minus 10 times 7, which equals 0. Here we only have one unknown, so rearranging for by, we get by equals 192 divided by 4, which equals 48 kilonewtons. Now we can substitute this value into our equation for the sum of all vertical forces, and doing so, we get ay plus 48 minus 40 minus 6 equals 0. So ay is equal to negative 2 kilonewtons. Having calculated the reaction forces, we will add them to the diagram. And doing so, at point A there is a horizontal reaction force of 10 kilonewtons acting in the left direction, and a vertical reaction force of 2 kilonewtons acting downwards. And then, at point B, there is a vertical reaction force of 48 kilonewtons acting in the upwards direction. Having calculated the reaction forces at the supports, we can now calculate the internal forces at points C and D. And starting with point C, we will cut bar AB in half, considering the left side. Doing this, we have a bar 2 meters in length, being supported by the hinge support at point A and ending at point C. We also have the loads being applied to this section as illustrated in the diagram. As for finding any unknown forces, we must annotate the unknown internal forces at point C. We will now reference back to our positive forces diagram, and for us, point C is the right side of the bar, so we will draw on the corresponding positive internal forces like so. Now, it's simply a case of applying the conditions of equilibrium, as we know that the section of the structure must still be in equilibrium. Taking the x-coordinate direction to be positive, the sum of all horizontal forces is equal to n minus 10, which equals 0. So we can instantly see that n is equal to 10 kilonewtons. Taking the y-coordinate direction to be positive, the sum of all vertical forces is equal to v minus 10 times 2 minus 2, which equals 0. So we can instantly see that v is equal to 22 kilonewtons. And finally, taking the anticlockwise rotation direction to be positive, the sum of all moments relative to point C is equal to 2 times 2 plus 10 times 2 times 1 plus m equals 0. So we can see that m is equal to minus 24 kilonewton meters. So we can conclude by saying at point C, there is a positive axial force of 10 kilonewtons, a positive shear force of 22 kilonewtons, and a negative moment of 24 kilonewton meters. To calculate the internal forces at point D, we simply just need to repeat this process. You're welcome to pause the video here to attempt this yourself if you feel confident enough to do so. Welcome back if you did attempt to calculate the internal forces in Part D. For this, we will cut the bent bar at point D and consider only the bottom section like so. Again, we must annotate the unknown internal forces at point D, and referencing back to our positive force diagram for a vertical bar, the corresponding positive internal forces look like this. Applying the conditions of equilibrium to solve for the unknowns, taking the x-coordinate direction to be positive, the sum of all horizontal forces is equal to -10 minus v, which equals 0. So we can instantly see that v is equal to -10 kilonewtons. Taking the y-coordinate direction to be positive, the sum of all vertical forces is equal to -2 minus 10 times 4 plus 48 plus n, which equals 0. So we can instantly see that n is equal to -6 kilonewtons. And finally, taking the anticlockwise rotation direction to be positive, the sum of all moments relative to point D is equal to -10 times 2 plus 2 times 4 plus 10 times 4 times 2 plus m, which equals 0. So we can see that m is equal to -68 kilonewton meters. So we can conclude by saying at point D there is a negative axial force of 6 kilonewtons, a negative shear force of 10 kilonewtons, and a negative moment of 68 kilonewton meters. Note also that this could have been done more easily by considering only the top part of the structure like so. I only chose to use the bottom part of the structure to demonstrate that you must use the entire part of the structure, not just up to the next support. When analysing the internal forces in truss elements, we saw that the internal forces were constant along the elements. However, this is not necessarily the case for internal forces in general structures. When analysing an element to ensure it will not fail, it is important to know the internal forces across the entire length, and to achieve this, we will need to introduce internal force diagrams. For this, we will consider a section of a bar which has a length tending to 0, or in other words, the length of the bar is arbitrarily small, and as a result of this, we will denote the length of the section to be dx. We will also assume that there are no concentrated forces or moments being applied to the section. Recalling the sensors for positive internal forces at either end of a bar, we can draw on the sensors for the positive internal forces at the left end of the section and the right end. And as we stated previously, the internal forces may not be constant along the length of the bar. If we were to denote the internal forces at the left end of the section to be V, N, and M, corresponding to shear, axial, and bending, respectively, then we must introduce a change in the internal forces for the right end. Using dV to denote the change in shear force across the section, dN to denote the change in axial force, and dM to denote the change in bending moment, we can denote the internal forces at the right end of the section like so. Finally, we will consider that distributed loads are being applied to the section. A distributed load perpendicular to the bar, denoted P, and a distributed load parallel to the bar, denoted N. Note here that because the length of the section of the bar we are considering is tending to 0, any change in the distributed load will be negligible, and so we can assume that the distributed loads are constant. Having established the conditions for our section of bar, we will apply the conditions of equilibrium. Equating the sum of all vertical forces to equal 0, we get -v minus p times dx plus v plus dv equals 0. The negative v cancels out with the positive v, giving us p dx equals dv, and then we can rearrange to get dv by dx equals p. Doing the same for the sum of all horizontal forces, we get -n minus n times dx plus n plus dn equals 0. And notice that this is the same case as we saw for the vertical forces, so we know that the equation is equivalent to dn by dx equals n. Finally, equating the sum of all moments in relation to the right end of the section to equal 0, we get -m plus v dx plus p dx times dx over 2 plus m plus dm equals 0. Again, the negative m cancels out with the positive m, so we get v dx plus p over 2 times dx squared plus dm equals 0. Here we can simplify our equation. As dx is very small in length, we know that dx squared is a significantly smaller quantity than any of the other quantities in the equation, and so it can be neglected, removing this entire term and giving us negative v dx equals dm. And now we can rearrange to give us dm by dx equals negative v. Therefore, we can conclude that the derivative of the shear force is equal to the distributed load perpendicular to the bar. The derivative of the axial force is equal to the distributed load parallel to the bar, and the derivative of the bending moment is equal to the negative of the shear force. And so we can summarise this conveniently in a table. But before we fill in this table, let's quickly revisit simple differentiation. Considering a cubic function, x cubed, its derivative is equal to 3x squared. So we know that the derivative of a cubic function is a parabolic function. The derivative of 3x squared is 6x, so the derivative of a parabolic function is a linear function. The derivative of 6x is 6, so the derivative of a linear function is a constant, and the derivative of 6 is 0, so the derivative of a constant is just 0. Now we can use this to easily compute our table. With a shear force of 0, the bending moment will be constant, as we know the derivative of the bending moment is equal to the negative of the shear force, and here the derivative of a constant is equal to 0. With a distributed load of 0, the shear force will be constant along the section, and bending moment will be linear. With a constant distributed load along the section, the shear force will be linear, and the bending moment will be parabolic. And finally, with a linear distributed load along the section, the shear force will be parabolic and the bending moment will be cubic. And for completeness, we will conclude that for a bar from point A to point B, the difference in V between A and B is equal to the area of P between A and B. The difference in M between A and B is equal to the negative area of V between A and B. The slope of V is equal to P, and the slope of M is equal to negative V. These are the cases for moving along a bar from left to right, but if you are moving along the bar from right to left, it's simply a case of inverting the signs in these equations. When drawing internal force diagrams, it will be important to use the correct convention for positive and negative forces. For structural analysis, it is common knowledge that a shear force diagram is represented upside down, where a positive shear is represented below the bar and a negative shear is represented above the bar. Likewise, for the bending moment diagram, a positive bending moment is represented below the bar and a negative bending moment is represented above the bar. And then an axial force diagram is the opposite, where a positive axial force is represented above the bar and a negative axial force is represented below the bar. So it's all well and good knowing this information in table format, but let's have a look at applying this theory to a simple example. Consider this 3 meter long bar, which is supported by a hinge support at point A and a roller support at point B. Additionally, there is a uniformly distributed load of 4 kilonewtons per meter being applied to the entire length of the bar. The first step for us is to calculate the support reaction forces. For this simple case, we can see there are no horizontal reaction forces or bending moments at the supports, and as the distributed load is uniform and being applied to the entire length, the vertical reaction forces will be the same at each support. Therefore, assuming sensors for the vertical reaction forces, taking the y-coordinate direction to be positive and equating the sum of all vertical forces to equal 0, we have 2ry minus 4 times 3 equals 0. So 2ry equals 12, and therefore ry equals 6 kilonewtons. So we can apply this to our diagram now, giving us vertical reaction forces of 6 kilonewtons at each support, both acting in the upwards direction. At this point, we will insert our diagram for the positive sensors for internal forces, which we will call our starred diagram for reference throughout the question. Let's start by analysing the left side of the bar at point A. At point A, the first force is the vertical reaction force of 6 kilonewtons acting upwards. Referencing our starred diagram, we can see that at the left end of the bar, positive shear forces act downwards, and so the reaction force of 6 kilonewtons causes a shear force of negative 6 kilonewtons. Now, moving along the bar from left to right, we only have a uniformly distributed load, or in other words, a constant distributed load. From our table previously, we know that if the distributed load is constant, the shear force will be linear, and the change in shear force is equal to the area of the distributed load. Additionally, as the distributed load is being applied in the downwards direction, which is positive for the left-hand side, the shear force will increase. To calculate the change in shear force from point A to point B, we need to calculate the area of the distributed load from point A to point B, which for this constant distributed load is simply 4 kilonewtons per metre times 3 metres, which equals 12 kilonewtons. As we know that the shear force increases from point A to point B, we can work out that at point B, the shear force will be equal to -6 plus 12, which equals 6 kilonewtons. So remembering the convention used for internal force diagrams, the shear force diagram looks like this, where the shear force increases linearly from -6 kilonewtons at point A to 0 kilonewtons at the centre of the bar and to +6 kilonewtons at point B. Now, moving on to the bending moment diagram, starting at the left end of the bar, there are no moments applied to point A or to the left of point A. Likewise, there are no forces applied to the left of point A that could cause a bending moment at A. Therefore, the bending moment at point A is 0. Moving along the bar, after point A, the bending moment is equal to the negative of the area of the shear force diagram. From point A to the centre of the bar, the shear force is negative, which means that the bending moment increases, and then from the centre of the bar to point B, the shear force is positive, meaning the bending moment will decrease. Remembering our principles that the shear force is the derivative of the bending moment, and as the shear force is linear, the bending moment is therefore parabolic. Also remember that the slope, i.e. the gradient of the bending moment, is equal to the shear force. So at point A, the slope of the bending moment will be increasing at a rate of 6 kilonewtons. At the centre of the bar, the bending moment will be horizontal as the shear force is equal to 0, and then at point B, the slope of the bending moment will be decreasing at a rate of 6 kilonewtons. As the shear force is linear across the bar, the area below the shear force diagram can be easily calculated using the formula for the area of a triangle. Between point A and the centre of the bar, the area is equal to 6 times 1.5 times 1/2, which equals 4.5 kilonewton meters. And as we know that the bending moment at point A is equal to 0, we know that the bending moment at the centre of the bar is equal to 0 plus 4.5, which is just 4.5 kilonewton meters. Applying the same process, the area of the shear force diagram between the centre of the bar and point B is equal to 6 times 1.5 times 1/2, which again equals 4.5 kilonewton meters. Now we can subtract this from the bending moment at the centre of the bar to get the bending moment at point B, which equals 4.5 minus 4.5, which equals 0. Again, remembering the convention used for internal force diagrams, the bending moment diagram looks like this, where the bending moment increases parabolically at a rate of 6 kilonewtons at point A, and then decreases at a rate of 6 kilonewtons at point B, reaching a maximum bending moment of 4.5 kilonewton meters at the centre of the bar. Note that for this example, there are no axial forces as none of the forces applied to the bar had horizontal components. Therefore, there is no need to draw the axial force diagram. However, if we were to draw it, it would look like this, with a 0 in the centre to denote the fact that there is no axial force along the bar. So there we have seen how we can determine the internal force diagrams for a simple structure containing a single bar. To finish off the video, we will work through an example for a more complicated structure. This structure is being supported by fixed support at point A and has a free end at point C. A uniformly distributed load of 8 kilonewtons per metre is being applied in the downwards direction to the entire length of the bar from point A to point B, and a concentrated load is being applied to the free end of the structure at point C. This concentrated load has a magnitude of 10 kilonewtons and is acting in the right direction. Again, we will be determining the internal force diagrams for the entire length of the structure, from point A to point B and from point B to point C. If you are happy in your understanding of the previous example, why not pause the video here and see if you can solve this problem on your own. Okay, welcome back if you did attempt this on your own, but now let's go through it together. We will start off by calculating the support reaction forces. For this structure, we only have one support, which is fixed, and therefore we will get a horizontal and vertical reaction force and a reaction moment. To calculate these, we will apply the conditions for equilibrium, where the sum of all horizontal forces must be equal to 0, the sum of all vertical forces must be equal to 0, and the sum of all moments relative to a point, which we will choose to be A, must be equal to 0. Taking the x-coordinate direction to be positive, the sum of all horizontal forces is equal to Rx plus 10, which equals 0. So we can see that Rx is equal to negative 10 kilonewtons. Taking the y-coordinate direction to be positive, the sum of all vertical forces is equal to Ry minus 8 times 4, which equals 0. So therefore, Ry is equal to 32 kilonewtons. Finally, taking the anticlockwise rotation direction to be positive, the sum of all moments relative to point A is equal to negative Rm minus 8 times 4 times 2 minus 10 times 3, which equals 0. So Rm is equal to negative 64 minus 30, which equals negative 94 kilonewton meters. Applying this to our diagram now, at the fixed support we have a horizontal reaction force of 10 kilonewtons acting towards the left, a vertical reaction force of 32 kilonewtons acting in the upwards direction, and a reaction moment of 94 kilonewton meters acting in the anticlockwise rotation direction. Having calculated the support reactions, we will insert our diagram for the positive sensors for internal forces, which we will call our starred diagram for reference throughout the question. Let's start by analysing the left side of the structure at point A. At point A, the first force is the vertical reaction force of 32 kilonewtons acting upwards. Referencing our starred diagram, we can see that at the left end of the bar, positive shear forces act downwards, and so the reaction force of 32 kilonewtons causes a shear force of negative 32 kilonewtons. Now, moving along the bar from left to right, we only have a uniformly distributed load, or in other words, a constant distributed load. From our table previously, we know that if the distributed load is constant, the shear force will be linear, and the change in shear force is equal to the area of the distributed load. Additionally, as the distributed load is being applied in the downwards direction, which is positive for the left-hand side, the shear force increases. To calculate the change in shear force from point A to point B, we need to calculate the area of the distributed load from point A to point B, which for this constant distributed load is simply 8 kilonewtons per metre times 4 metres, which equals 32 kilonewtons. As we know that the shear force increases from point A to point B, we can work out that at point B, the shear force will be equal to negative 32 plus 32, which equals 0 kilonewtons. So at point A, the shear force is equal to negative 32 kilonewtons, and at point B, the shear force is equal to 0, and the shear force increases linearly from point A to point B. Therefore, the shear force diagram will look like this from point A to point B. Now we need to do the same from point B to point C. There is no distributed load being applied to the bar from point B to point C, and therefore, remembering back to our table, the shear force must be constant along the bar. To calculate this constant value, we must determine the shear force that is being applied to the entire length of the section. For this case, the only force being applied to bar BC is the horizontal force of 10 kilonewtons acting in the right direction. Therefore, we need to calculate the component of that force that is acting perpendicularly to the bar, and for this, we will use trigonometry. As bar BC has a horizontal and vertical length of 3 meters, we know that the angle between bar BC and the horizontal plane is 45 degrees. Now, if we were to draw on the component of the horizontal force that is perpendicular to the bar, we can see that we know the value of the hypotenuse side, which is 10 kilonewtons, and we are trying to find the value of the adjacent side. So using trigonometry, we can calculate that the magnitude F is equal to 10 times cosine 45, which equals 7 kilonewtons rounded to the nearest integer. And this is the constant shear force that is being applied to bar BC. Now revisiting our starred diagram, the shear force of 7 kilonewtons is being applied from the right end of the bar. So comparing our diagram to the starred diagram, we can see that the shear force of 7 kilonewtons is negative. Now that we know this, we can add the constant shear force to our shear force diagram, and doing so, we get the following. where the shear force along the bar from point B to point C is constantly -7. Note that due to the convention for internal force diagrams, negative shear forces are drawn above the bar. Now moving on to the bending moment diagram, starting at the left end of the bar, we have a moment of 94 kN acting in the anti-clockwise rotation direction being applied to point A. Referencing back to our star diagram, for the left side of the bar at point A, a positive moment acts in the clockwise rotation direction, so therefore we know that the moment of 94 kN acting in the anti-clockwise direction will result in a bending moment of -94 kN in the bar at point A, and so we can plot this on our bending moment diagram like so. Moving along the bar, after point A, the bending moment is equal to the negative of the area of the shear force diagram. From point A to point B along the bar, the shear force is negative, which means that the bending moment increases. Remembering our principles, the shear force is the derivative of the bending moment, and as the shear force is linear, the bending moment is therefore parabolic. Also remember that the slope, i.e. the gradient of the bending moment, is equal to the shear force. So at point A, the slope of the bending moment will increase at a rate of 32 kN, and then, at point B, the slope of the bending moment will be flat, as along bar AB, the shear force at point B is equal to 0. As the shear force is linear across the bar, the area below the shear force diagram can be easily calculated using the formula for the area of a triangle. Between point A and point B, the area is equal to 32 times 4 times 1/2, which equals 64 kN. And as we know that the bending moment at point A is equal to -94 kN, we know that the bending moment at point B is equal to -94 plus 64, which equals -30 kN. So we can plot this on our diagram as well, remembering that the bending moment is increasing at a rate of 0 at point B, i.e. it is flat. Now we can simply connect the two plots with a parabolic curve like so. The bending moment diagram from point B to point C is a little bit simpler, as the shear force is constant along bar BC. Starting at the left of bar BC, at point B, we have a bending moment of -30 kN, as we have just worked out for the previous section, so we will plot this on our bending moment diagram like so. Moving along the bar, from point B to point C, the shear force is negative, which means that the bending moment will increase, and after point B, the bending moment will be equal to the negative of the area of the shear force diagram. Remembering our principles, the shear force is equal to the derivative of the bending moment, and as the shear force is constant, the bending moment is therefore linear. Also remember that the slope, i.e. the gradient of the bending moment, is equal to the shear force. So, at point A, the slope of the bending moment will be increasing at a rate of 7 kN, and then, at point B, the slope of the bending moment will also increase at a rate of 7 kN. And this makes sense because the linear property of the bending moment diagram means that it will change at the same rate along the entire length of the bar. As the shear force is constant along the bar, the area below the shear force diagram can be easily calculated using the formula for the area of a rectangle. We already know that the height of this rectangle is 7 kN, but we need to know the length as well. For this, we will use Pythagoras theory, where the square root of the length of the adjacent side squared plus the length of the opposite side squared is equal to the length of the hypotenuse, which is just the length of bar BC. Doing this, we get that the length of bar BC is equal to the square root of 3 squared plus 3 squared, which equals 4.24 meters to 2 decimal places. Now we can calculate the area of the shear force diagram, which equals 7 times 4.24, which equals 30 kilonewton meters, rounded to the nearest integer. As we know that the bending moment diagram at point B is equal to -30 kilonewton meters, we can work out that the bending moment at point C is equal to -30 plus 30, which equals 0. So again, we can plot this on our diagram, remembering that the bending moment is increasing at a rate of 7 kilonewtons at point C. As we know the bending moment increases linearly from point B to point C at a constant rate of 7 kilonewtons, we can draw this onto our diagram, giving us this final bending moment diagram. Finally, we must determine the axial force diagram. To determine the axial force diagram for bar AB, as we have seen before, we must cut the bar isolating one part of the structure and then solve for equilibrium. Cutting the bar at the midpoint of AB and then isolating the left part of the structure, we have this diagram. And now, referencing back to our start diagram, we can draw on the positive sensors for the internal forces at the cut end of the bar, denoting them V for shear force, N for axial force, and M for bending moment. As we are only trying to find the axial force though, we only need to worry about N. Applying the conditions for equilibrium and taking the x-coordinate direction to be positive, the sum of all horizontal forces is equal to N minus 10, which equals 0. So we can see that N is equal to 10 kilonewtons. Therefore, the axial force at the centre of the bar is equal to 10 kilonewtons, and as this is positive, we know that it is a tensile force acting away from the centre of the bar. Additionally, from the diagram of the structure, we can see that no axial loads are applied to the structure between points A and B, so the axial force will stay constant from point A to point B, and the axial force diagram will look like this. Noting that the convention for this diagram is that the positive axial force is above the bar and a negative axial force will be below the bar. And now, the last step is to carry out the same process for bar BC. Cutting the bar at the midpoint and then isolating the right part of the structure, we have this diagram. Again, referencing back to our start diagram, we can draw on the positive sensors for the internal forces at the cut end of the bar, denoting them V for shear force, N for axial force, and M for bending moment. And as we are only trying to find the axial force, we only need to worry about N. Earlier on in the question, we used trigonometry to calculate the shear component of the 10 kilonewton force, and now we are going to do the same to find the horizontal component to the axial force in terms of N. Having drawn the diagram for the angle between the axial force, N, and the horizontal plane, and having drawn on the horizontal component of N, it will now be easier to derive an expression for it in terms of N. Using trigonometry, we know that the adjacent side divided by the hypotenuse side is equal to the cosine of the angle, and therefore we can rearrange for our hypotenuse side, f, such that f is equal to n divided by cosine 45. Now we can apply the conditions for equilibrium, where taking the x-coordinate direction to be positive, the sum of all horizontal forces is equal to 10 minus n over cosine 45, which equals 0. So rearranging for n, we get n equals 10 times cosine 45, which equals 7 kilonewtons. Therefore, we can conclude that the axial force at the middle of bar BC is 7 kilonewtons, and since it is positive, it is a tensile axial force. Again, from the diagram of the entire structure, we can see that no axial loads are being applied to the structure between points B and C, so the axial force will stay constant from point A to point B, and we can draw the axial force diagram like so. And now we have completely determined the internal force diagrams for this structure. To summarise what we have covered in this video, we started by introducing the types of internal forces within an element of a structure, then learning the positive notations for the internal forces within a bar. Next, we covered how to calculate the internal forces at a specific point within an element. We then introduced the concept of internal force diagrams, along with the principles for determining the degree of each internal force along a bar, and the conventions for internal force diagrams. And we finished the video off with 2 example problems where we implemented all of the theory we had previously learnt. This has been a video by Learn Civil Engineering. If you have found this video useful at all, please leave a like and subscribe to the channel to show your support. If you do have any remaining questions or would like me to cover a specific topic, please leave them in the comment section below and I will try to respond as soon as possible. Thank you for watching.